Good day everyone, I am Miguel Santiago. Together I am with Alihan, Jos, and Nicodemus Joseph. Today we'll be talking about differential equations and why they are so important, especially in the field of engineering. First, differential equations are mathematical expressions that involve derivatives. In simple terms, they show how a certain quantity changes over time. These equations help us understand dynamic systems. They are just not for textbooks. Differential equations are used to model, predict, and control real-world problems or systems. We'll find them in biology, physics, and especially in engineering. In engineering, they are vital in designing and analyzing things like bridges, buildings, and aircraft. By using differential equations, engineers can predict how these structures will behave under different conditions. More than just giving answers, these equations help improve efficiency, ensure safety, and provide insight into how different parts of a system affect each other. They reveal patterns that might not be obvious at first glance.
Engineers use differential equations to solve beam deflections problems to make sure structures are safe and long-lasting. This is important in both civil and mechanical engineering, especially when designing buildings, bridges, and other structures. Beam deflection is how much a beam moves when a load is applied. Engineers also need to understand and predict this to avoid damage. If beam deflection is not calculated correctly, it can lead to serious problems like cracks, deformation, or even collapse. This can put life at risk and cause expensive repairs. Structures must handle everyday use and extreme events like earthquakes and other natural disasters, which is why accurate calculations are critical. By using differential equations, engineers can design stronger, safer, and more cost-effective structures. It helps reduce risk and ensures that the structure will perform well over time.
For its practical application, the differential equation for lateral beam deflection is denoted by the following equation: d raised to 4y over dx raised to 4 plus a squared e squared y over dx squared equals w over ei, which is the equation 1, where a squared equals w over ei, w equals axial load, w equals lateral load, and ei equals flexural rigidity. The general solution for this type of equation would be expressed as y of x equals y sub c plus y sub b, which can be used on the equation 1, and which can be used on d raised to 4 plus a squared d squared times y equals 0, which can be formed into m raised to 4 plus a squared m squared equals 0, which is m equals 0, 0 plus minus ai, and then y sub c equals c sub 1 e raised to 0x plus c sub 2 x e raised to 0x plus e raised to 0x c3 cosine ax plus c sub 4 sine ax, and then c equals c sub 1 plus c sub 2x plus c sub 3 cosine ax plus c4 sine x, which is the equation 2 for this equation. Once the complementary solution y sub c is obtained, the particular solution will be y sub p, determined next as presented in equation 3. R of x equals w over ei, which is then formed into y4 prime sub p equals 0. Going back to equation 1, it can be written as c as 2a squared equals 2wc sub 5 over ei equals w over ei, where c sub 5 equals w over 2w, which we can further simplify into equation c sub 5 equals w over 2w, and then y sub p equals c sub 5 x squared equals wx squared over 2w, which we will call equation 3.
For equation 4, to cancel out the constants in the latest equation, we can establish boundary conditions as can be observed in figure 1. So figure 1, boundary conditions of lateral beam deflections. Applying figure 1's conditions to equation 4, we can further simplify the equation as yx is equal to w 1 minus alpha l sine alpha x over alpha squared w cosine alpha l times cosine alpha x minus 1 plus wl over alpha w times sine alpha x minus alpha x plus wx squared over 2w. In equation 5, where alpha squared is equal to capital W over ei, and capital W is equal to the axial load, and small w is equal to the lateral load, and ei is equal to flexural rigidity, and lastly, L is for length.